Reference circle. Simple harmonic motion can be described in terms of displacement, velocity, and acceleration. So we can observe with this figure that a sinusoidal motion follows a uniform circular motion. So this uniform circular motion on a path known as the reference circle. So meaning all simple harmonic motion has a corresponding uniform circular motion path or a reference circle. And it is applicable when the radius of our uniform circular motion is equal to the amplitude of the sign of the simple harmonic motion. So a simple harmonic motion is the projection of the uniform circular motion onto a diameter. So this circle is called the reference circle, and the rotating vector is called phasor. This blue arrow that you observe rotate around the circle is what we call phasor. So in describing this circular motion, we have this placement, which is equal to a cosine the angular frequency times time, wherein the angular frequency can be defined by the square root of the spring constant over the mass. Same with the frequency and period that can be defined in terms of the spring constant and the mass. For the velocity, we have this equation or formula, which is equal to negative the amplitude of the times the angular frequency times sine angular frequency times time. Or for the maximum velocity, we have amplitude times the angular frequency. And in terms of acceleration, we have this formula, which is equal to negative amplitude times the square root of the angular frequency times the cosine, wherein the angle is the product of angular frequency and time. And for the maximum acceleration, we have the formula amplitude times the square root of the angular frequency. Now let's try to apply these formulas and equations in a problem. Let's say we have a diaphragm of a loudspeaker moves back and forth in simple harmonic motion to create sound. The frequency of the motion is 1 kHz and the amplitude is 0.2 millimeter. What is the maximum speed of the diaphragm? Where in the motion does this maximum speed occur? So to solve for the maximum speed or Vmax, we will use the formula A times the angular frequency. And we know that the angular frequency is equal to 2 pi f. And we have a given of frequency of 1 kilohertz and amplitude of 0.2 millimeter. So substituting the value, we have 0.2 times 10 raised to negative 3 meter times 2 pi times a frequency of 1 times 10 raised to 3 hertz. And we know hertz is equal to 1 over seconds. Cycle per seconds or 1 over seconds. Therefore, our Vmax is equal to 1.3 meter per seconds. For letter B part of the question, where in this motion does this maximum speed occur? The speed of diaphragm is 0 when a diaphragm momentarily comes to rest at either end of its motion. As you can remember with the simulation, we observe that at maximum height or maximum displacement or the amplitude, it has a velocity of 0. Therefore, in between the positive A and negative A, where is the maximum speed occur? In the midway of the range. Therefore, the maximum position or the maximum speed occur at x is equal to 0 meter. Okay, so let's have another example. Oh, sorry. Let's refer to the previous example problem. What is the maximum acceleration of the diaphragm, and where does the maximum acceleration occur? So the maximum acceleration is equal to A times the squared of the angular frequency, wherein our amplitude is equal to 0.2 times 10 raised to negative 3 meter times 2 pi, and the frequency is 1.0 times 10 raised to 3 hertz, or 1 over seconds squared. Therefore, our A max is equal to 7.9 times 10 raised to 3 meter per second squared. Now, for the part B, where does the maximum acceleration occur? So the maximum acceleration occurs when the force acting on the diaphragm is a maximum. Again, the maximum acceleration occurs when the force acting on the diaphragm is a maximum, following the Newton's law of motion that that acceleration is equal to force over mass, wherein force is equal to kx over m. Therefore, acceleration is directly proportional with the displacement. So the maximum acceleration occurs at the maximum displacement or at maximum amplitude. So therefore, at part B, x is equal to maximum or minimum amplitude. So in our case, in the problem, it is equal to positive or negative 0.2 millimeter. Now, let's try your understanding. Let's test your understanding by solving the next problem. It's kind of wordy, but I know you can understand this problem. So try to solve and write your answer in the comment section.